welcome everybody to our next DC Thursdays. I'm Pete Soderling. I'm the founder of Data Council and the Data Community Fund. And as you know, we've been producing these programs, these interviews every other week on Thursdays to talk to a leader in the open source data world. So today I'm very excited to have Stephan Ewen here. He's the co-founder and the CTO of Ververica, which is the core company behind Apache Flink. So Stephan, welcome.
Thanks, Pete, for having me.
Yeah, it's great to have you here. I'm in Wyoming, you're in Berlin, but through the wonders of the internet, we're able to do a COVID-safe session.
Right.
So tell me, what's the big idea with streaming? It seems like it's a paradigm shift. It's an architecture that is very different than the batch architecture that many companies are familiar with. It requires some new thoughts, some new thinking, all things that we'll discuss in the program. But I just wanted to ask you, like, what's the big idea here behind streaming?
Yeah, it's actually not, I think, one idea that's the thing that makes streaming big. I think streaming is where a few things finally like come together and form like a good whole big picture, which is what makes it so interesting. But let's actually go through a few of these things that motivate folks to use it. So I'd say the first thing that most people think about when they hear streaming is, sure, it's definitely a way to reduce the time to acting on the data, you know, rather than going with the batchy way of, you know, data gets produced, you keep gathering it for a while, ingesting it into some data lake or so, and then you run your analysis maybe end of the day or so. Streaming really continuously processes and acts on the data. So it's definitely it's definitely a great way to say I want to, you know, like reduce the time to action for my data. But it's not just that. It's if it were just that, then it would be, you know, like a second thing that you add in addition to what you already have, you know. And that's kind of how it started, to be honest. Like there was the fast data path and the slow data path. But I think when you talk about like streaming today, maybe it's kind of like the second or third generation of streaming, people sometimes call it. It's this yeah, like you said, it's a different paradigm to think about data. It's a way to really model and treat data as this continuous sequence of events, which is quite natural because mostly that's really how data is produced, you know, like as events coming from a user interacting with a service, coming from a sensor or a device, producing a reading and so on. And yeah, and streaming, you really acknowledge and kind of embrace this nature, and then model your applications as processing of these events, right? Batch has in some way a bit of a simplifying, but also a bit of an unnatural assumption, right? Like here's a terabyte of data. A terabyte of data there's not a terabyte of data appearing out of nowhere. It usually was a stream at some point in time that you gathered and, you know, batched up before you processed it. And in streaming, you kind of skip the step. You go directly on working on the data as it's naturally produced. And this is, if you start to model your applications like this, it's a very both a natural way once you start embracing this, and it's also kind of a unifying way, because you can still actually do the batchy processing of data. You can still, if you wish, like take the stream and buffer it up in your message queue in a data lake and still process it as a batch. But because you started to model and treat it like a stream, you could also just switch it around and say, I'm not buffering and batching it up. I'm acting really on the events as they come. So you have kind of this paradigm that allows you to do both things, depending just on a configuration almost, if you wish. And that's very powerful.
Well, I know that's one of the things that we'll talk about today is this notion of actually being able to use Flink as both a stream and or a batch processor, which is something that I know you're excited about. I don't think that's something that Flink supported in V1. So we want to talk about that today. Before I continue, I want to ask you about the origin story of Flink. But I also want to mention to the audience and remind them that if anyone has questions, we've been having a lot of fun doing sort of audience guided discussions over the last couple episodes. And so if you have questions for Stephan about Flink, about streaming in general, please drop them in the YouTube chat comments, and I'll be taking questions as we go along. So that's a fun way to affect the conversation from your end. So Stephan, before we get into some more of the nitty-gritty details architecturally about Flink, which I'm excited to hear, tell me about the origin story. Like how and why did Flink come to be?
Yeah, yeah, that's an interesting one. So in some sense, Flink is a university research project spin-off. Started out with a bunch of people, most of who later became early committers and PMC members of Flink, and also founders of back then Data Artisans. We were working at the university in Berlin on a research project, and the way it started out, it was very, I could say, vaguely defined. Hadoop was just a cool thing back then, and the project just set out and said, okay, Hadoop is pretty cool, but also it kind of dropped, let's say, 20, 30 years of results of technology and research results from the database community. So let's try and see if we can kind of bring these things together a bit. And then
what year was this, Stephan? Was this 2012 or
29 actually?
2009. Wow.
Was when that started. It was not Apache Flink back then. It was a research project called Stratosphere. Yeah, so we were working on this at the university, and that's kind of how the project started out. But it kind of took a bit of a different direction then, because how these projects go, and it actually ended up with us building a system for diverse use cases of data processing with kind of a somewhat of a streaming backend, even though streaming wasn't a big thing back then. I think Storm was just starting to become a known project. And in the end, we actually did have a batch processor with a streaming backend in the end. That was the result. It sounds a bit strange, like why would you do that? But there's actually some interesting properties to that. And for a research project, it made a lot of sense back then, especially for the use cases we wanted to look at. So we're actually quite excited about the result of this project, and we're thinking, okay, let's see what we can do out of this. And so we took this to the Apache Software Foundation with a few initial users and committers, and started working on this. And I think during the first year when we were working on this, I think this is when the idea of streaming started to become really more crisp and popular. Not just in our heads. I think this is I think both the adoption of Storm was there. I think Spark Streaming was released during that time, and I think Kafka version 08 or so just came out, and you could see people becoming really interested in that. But also there wasn't really a good stream processor around. These concepts of event time were basically, I think, nowhere yet, other in a few Google research papers. This notion of being able to do exactly once, both with low latency and high throughput, there wasn't really a system out there that could do that. And we realized that we actually had a pretty interesting thing in our hands, which was fairly close without actually doing this, right? The backend was actually very, very well designed to handle these challenges. It's just we never exposed any of that, because the use cases we were looking at were very much batch use cases actually. And then we realized that let's just try and make an experiment and put a streaming API there, just see if that's interesting to somebody. And it was very surprising. It was very, very interesting to a lot of people because of this exactly once low latency high throughput notion you could get, because of the flexibility and the event and time model that we were able to quickly manage. Google Dataflow was published, I think, as an open source SDK during that time. We're pretty quickly able to integrate with that, because all these concepts just matched really well between the systems. And so I think that's kind of how Flink came to be a streaming system, even though it's actually, if you think about it, a batch project when it started.
And then you started Ververica in around 2014, I guess?
That's right, yeah. It was not called Ververica back then. It was called Data Artisans. That's the name of the company we started, right? That was 2014, maybe half a year after we open sourced the project under the umbrella of the Apache Software Foundation.
Got it. And how do you see people using Flink today? What are the main use cases where somebody would sort of take this plunge into streaming? Because I still feel like, even though,
Mm.
like you said, we're probably in the third generation or so of streaming tech, and there's many options out there, as we all know, many competing options, which I'm sure you have insights on. What's the tipping point for most folks in, like, what's the most common use case for them to actually dive in and get their feet wet with streaming? Like, what does that typically look like from your perspective?
Mm. I would say this is changing also a little bit. Like, what are the common use cases? I would say till a little bit ago, one of the predominant use cases that folks just looked at doing were certain things like low latency, fraud detection, anomaly detection. Something that was known under maybe as a CEP if you go a decade back or so. But the CEP engines from back then were a bit like rigid, often not very scalable. But you
CEP?
can complex event processing. Sorry, yeah. So that meaning you have a set of rules or so or patterns that you want to search for in your data stream, things that may indicate an anomaly, a network intrusion, financial fraud, or just, I don't know, a bunch of sensors going off in an irregular pattern, and something you want to take a look at. So that was one of the very common use cases. Another one, I would say you could almost think of it as like real-time ETL or real-time dashboards or so, where users were subscribing to some event sources and they wanted to render dashboards and charts in real time, or move it in real time to another database for up to date BI queries or something like that.
This could be potentially for like analyzing clickstream data. That seems to be a common use case that I hear folks implement streaming systems for. Is that right?
Yeah, absolutely. So I think from that time came most of the, I would say, use cases that are very well known. So fraud detection, I mentioned that one. I think the clickstream one you mentioned is very present in a bunch of use cases around real-time recommendations. So a lot of like online platforms that want to give you real-time content recommendations based on your current interaction and not just on what they figured out you were doing a week ago, because your mood today might be different than your mood a few days before, so you're interested in different content. In fact, one of the biggest use cases that we get in touch with Alibaba about was one of those. Like, their entire e-commerce platform is, the search is, if you wish, one giant real-time recommendation system running on Flink. So so those were definitely big use cases. I would say others that got also somewhat popular were things around that dynamic supply and demand matching. So let's say you have a ride-sharing app or so, and you're interested in or it wants to suggest a price and take lots of things like forecasted supply and demand, traffic patterns, and so on into account, to compute these things continuously in the background, like the parameters based on which these suggestions are then made. Those were definitely the popular use cases, and I would say they still are. Maybe I shouldn't say that in the past tense. What I would like to add is, in some sense, one that we see coming up now more and more is this whole idea of like unified real-time and batch analytics. So I guess this is partly also due to the new capabilities of Flink, that it's really added a lot of, even though it came from the batch side, when we worked on the streaming side, you're not paying too much attention to the batch side for a few years, but we've actually added like a lot of sophistication there over the last 2-3 releases again. So partly due to these changes, and I'd say also due to the rising popularity of SQL in the streaming world. These use cases are very strong right now. So being able to build like a unified real-time and batch analytics system, just based on a high-level language like SQL, is, I'd say, one of the prime use cases right now.
That's fascinating. Well, that's probably a good segue. I want to open up the Flink API diagram that we discussed. Let me just put that on the screen, and I think I want to give you an opportunity to chat through that. There we go. So can you talk us through this API stack, because I found this particularly interesting, and I'm hoping it gives you an opportunity to talk about some of the architectural decisions that you made when you were designing Flink as well.
Yeah, sure. I think this is a good way to start talking first through the, let's say, the API user-facing perspective, and then maybe a little bit through the like runtime architecture and an operational perspective. Yeah. So, yeah, in this API stack, I think you can kind of see that there's different entry points to Flink depending on the trade-off between expressiveness and flexibility versus let's say conciseness, declarativity, ease of use. Maybe we start from the bottom. The first things we're really working on were with these basic building blocks that I think that give you an amazingly great flexibility and still take a lot of problems away from you. Just having very powerful ways of dealing with events or event streams, state, and various notions of time. And based on that, you can model a lot of things. You can build your unified applications. You can build your you can build real-time trading systems, alerting systems, and so on. But you're in a bit of a low-level world there, because you're really asking the user to say, okay, model your Java, Scala classes and so on for your events, decide when to put something into state, draw it out of state again, when to schedule timers for callbacks and so on, how to deal with differences between event and processing time. It's very powerful, but it requires quite a level of understanding of the model. In the data stream API, most of this is exposed, but it gives you a few also, let's say, shortcuts to just define time windows. Something like tell me what the the average number of visits was in the last 5 minutes. But still a very let's say physical way of programming where you're dealing really with Java and Scala code and so on. Up from there, we're with the efforts to say, okay, let's make this a bit easier and accessible to a broader audience. And I think we can really say mostly the SQL API and the table API are the same. SQL is the textual representation, if you wish. The table API is a domain-specific embedded language, but pretty much with the exact same expressivity and idea. So you're dealing with tables, with a logical schema, with logical operations. Everything goes through an optimizer that deals with the details for you. So if you go to this API, you're taking a slightly different abstraction level. You're now not looking at the individual events anymore, but you're looking at the concept called like dynamic tables. So I think we can go into details of that in a bit. And then kind of recently, I would say maybe less than a year ago, Python came in the mix, and just because we just saw it was very popular with a lot of users, was I think one of the most requested features. And the first way we've integrated with Python is actually as a way to define user-defined functions in SQL and in the table API in Python. If you want a custom aggregate function or a custom table function or a custom Scala function and so on, you can write these in Java, Scala, and now also in Python. And I think gradually we'll extend the support and also add Python support for the lower levels of the stack. At the moment, Python only supports the higher levels of the stack.
I see. That's great to know. I was not aware that Flink had Python support now, at least at that layer. So that's super interesting. And I'm sure that makes the platform much more easy to use and to adopt by a broader set of different types of users who don't necessarily want to muck around with the Java JVM.
Yeah, absolutely. I mean, especially in the machine learning world, Python is very, very popular. And part of this, like this vision we have for Flink to build this unified system where you can run, let's say, batch computation and streaming computation interchangeably. It makes it also, I think, very, very attractive in the long run as a system for a bunch of machine learning workloads. Where on the batchy side you have the training of the model, on the streaming side you have the, let's say, real-time feature vector assembly and evaluation of the model. And so as a way to like look at these use cases, yeah, that was one of the big reasons of why we also added Python support, because I think these are going to be very interesting use cases for a unified system.
Got it. Well, let's dive into that a little bit more, because I'm sure the audience is very curious to hear about this, the support, this dual support for both batch and stream. Can you walk us through the basic architecture? And I wish I had another diagram, but can you walk us through the basic architecture of how that all fits together?
Yeah. So maybe I can quickly start again. Like, what does it mean to use a unified system from the programmer's perspective, and then see like how does a unified runtime actually look? Because that is interestingly actually that can be quite different. So unified APIs, this idea has actually been, I think, around for a bit. With projects like Hummingbird from Twitter that offloaded parts of the data to Storm, parts of the data to Hadoop, projects like Beam that look at unified APIs, and Flink is also doing this. What's, I think, fairly new is this idea of using SQL for a unified system. And then there are a bunch of systems that try to implement really a unified runtime, one that can do both batch and streaming at the same time. And I think that their Flink's pretty unique actually. But taking a step back from the runtime and looking first at the abstraction level, I think SQL is a very interesting way to maybe try and describe this. So if you look at how SQL is defined, it's you have a SQL query that takes a bunch of tables, and the result of the SQL query is again a table. That's like the relational model. Some relations go in. You have the query with some filters, you throwing out some columns, your joins, doing some joins, some aggregates, and the result's again a table. In some sense, that's a batchy model, right? You're taking a static set of data, a fixed table in, and you're getting a fixed table out. So I think that's also why it was such a good match for the batch processors, right? Why Hive became so popular, Spark SQL, and so on. It turns out actually SQL has a pretty cool meaning in the streaming world as well, and that is if you start to think of a table not as a static thing, but a table as something that changes over time. Like a table might, there might be a row inserted into the table, a row deleted from the table, a row updated to the table, and there's actually very interesting ways to interpret a stream as a table that is undergoing changes. I think Kafka has for example talked about this notion like stream table duality for a while, and this is really also what I think the idea of streaming SQL takes, if you wish, to the next level. So you take a stream of events. Let's say these events, they can go by a primary key and replace other entries by primary key, or they can also really encode operations like updates, inserts, and deletes. And then you arrive at a set of table that changes. As new events through the stream come, this table changes. And then we run a SQL query over this changing table, and this actually produces a result table that's not static, but that's also changing. Let's say the SQL query is something like, I don't know, tell us the best-selling project in the geography, or so, the best-selling product in the geography of the day. And as new events come in, this might actually change, right? So before it used to be, I don't know, white tennis socks, and now it's actually whatever, I don't know, Nike trainers or so. And so that's really what the SQL query would then tell you, right? As the incoming relation changes, it would tell you, okay, take away from your result set that pair of tennis socks, and add into your result the Nike trainers or so, because the result just changed. And that's actually a very that's a model that a lot of people can get actually used to. Just thinking of SQL as not static table to static result, but dynamic table to dynamic result. And then it's really the question, what do you do with this dynamic result? You can of course like put it in another database over which from where you visualize it in a dashboard, or you can convert it back to a stream that says, change most popular product from this to that, or you can use it to define actions on, if that happens, then trigger this alert and so on. So that's really a way to think of let's say unification of the analytics from the API perspective. And the nice thing is this is so well defined actually in the end that if let's say you have the stream of events that produces the table, you run this incremental stream to dynamic table, dynamic streaming SQL query, and dynamic result. If you run through the entire stream, you get a final result. If you actually just gather the whole stream, materialize it in one table, and then run a batch query, you get the exact same result. So it's really a way of saying we're continuously computing this, incrementally updating the result, adding your items, taking items out, rather than saying we're first of all waiting to ingest all data, put it there, and then we're running it in one batch. And I think this is a good example to show how to really use this notion of streaming. And we didn't add something new here. We just kind of generalized the existing. Right? You start with SQL and just generalize it from a static to a dynamic table. And a static table is kind of just a special case of a dynamic table in the end.
But of course, there's lots of other complexity like under the covers to be able to do all this, and sometimes an application can't wait for the full dynamic table to be like rematerialized, and so the applications, if you're building a true streaming application, there's things like windowing and sort of acknowledging like what's in a batch and other functions and concepts that are critical for streaming, right? I think your checkpoint system probably fits in here somewhere. Can you just walk us through some of those basic concepts for those of us who might be new to the streaming world?
Right. So I think what you said was really important. The thing that really makes streaming different is the fact that you have to acknowledge that if you're not looking at a static set of data, you do have to trade off your latency versus completeness, if you wish, right? If you wait a little longer, you have more data and you get a result that's closer to the final result, but it also takes longer to get the result, right? The earlier you ask for a result, the less complete it is, right? So that is exactly what requires kind of the flexible runtime architecture to be able to, if you wish, like dial this knob in the direction that you need. If you're interested in very low latency, then you get results that flow through extremely fast, but they might actually not even be relevant. They might be retracted later because they get replaced by newer results. And then if you're on the very extreme other end, on the batchy end, you don't emit anything. You wait really long until everything is there, and then you get it in one chunk. And that really requires. So in the APIs, this. If you go to the data stream API, you're configuring your watermarks, for example, just to throw this out there. This is exactly the modeling of this trade-off of latency versus completeness. That's the event time watermark.
Mm-hmm.
Going to the runtime level now, there's a bit of a difference in how you want to execute streaming versus batch queries in many ways. For streaming queries, it's quite important to keep the data running. You start every operator at the same time. An event comes in, it has to flow really fast through the data flow and produce a result. At least if you're asking for like very low latency results. For a batch processor, you can really also do this batchy processing one stage after the next stage after the next stage, because nobody's asking you for any results before everything is done. This actually turns out it's a very different. It boils down to very different algorithms in the runtime to do this efficiently, and also very different strategies for fault tolerance. And I think this is really where Flink came up with a pretty great idea. Like traditionally, the batch processors really just did batch processing, schedule tasks, recompute the task on failure. This is what Hyperloop does, Spark does, and so on. To some extent, also what Flink does. If you look at at pure streaming systems, for example, like Kafka, what they typically do is they take an event from a queue, process something, put it back into another queue. Now, both of these models don't really work for the other case. Like if you put something from a queue, process it, put it back from a queue, you can in theory do batch processing with that, but it's just going to be horribly inefficient. On the other side, the batch system doesn't even give you a chance of doing low latency processing. What Flink basically did is it came up with a good middle ground between those two things. It actually did build a pipelined system that really lets the events flow through really fast. And added a fault tolerance mechanism that doesn't require persisting the events in queues in the middle, but it added this checkpointing mechanism where you basically draw an asynchronous background snapshot view of the system, and then then recovery basically boils down to when you hit a failure, you analyze what operators are connected to that failure, and you do actually kind of a similar recovery as you would do for a batch system, but only back to the last checkpoint. And this actually gives you a very nice hybrid architecture, because for batch processing, what you do is you just don't run checkpoints. There's an implicit, if you wish, checkpoint at the beginning of the job, and tasks fall back to that. And then it boils down to the same thing that Hadoop and Spark and so on do. And for a streaming system, you just draw these snapshots really quickly. And every time an operator fails, like a small region rewinds to that snapshot and continues from there. So you have a very small amount of work that you do, that you go back to redo once you have a failure. And I think this characteristic is really what allows Flink to really scale pretty well to both types of use cases, to the batch processing and the stream processing use cases. And there was a bit of serendipity to discover that mechanism, admittedly, but it turned out to be actually, I think, like one of the very defining things for Flink.
And is this one of the core concepts behind Flink's stateful streams as well, or can you go into that just a little bit, because I think that's an important concept as well.
Right. Yeah. So I think when we talk about streaming today, we implicitly talk about stateful streaming. I'd say if we go back to how streaming started, there's a lot of stateless streaming, which in some sense just means you take events, maybe transform them and route them. And there's certain things you can do with that, like some simple forms of streaming ETL and so on, or using streaming to connect different systems, like move data in real time. That is possible, but the only thing you can really do is something that's like almost forgetful. You can think a bit about it like that, right? Every event is on its own. It only knows itself and its content. It doesn't know anything about like what happened before it, or so. And that really limits the use cases. For a lot of interesting use cases, you do want to know a bit about your context. Like, okay, I'm an event that is somehow suspicious. Am I the first one? Then it might be okay. But if I'm the third one in a row, this might be something I want to trigger an alert for. And this is really the state, like this context that every event has accessible, to know more than just itself, like to know something about what happened in the past. And if you don't have state, then things become really easy. Then recovery also doesn't need to recover much other than just like kind of needing to know where you left off and where you have to continue. If you have state, you have to really be careful and correlate where were you in the stream, what is the changes to your state and to your context. This is really what you need checkpointing for. If you don't have stateful stream processing, you don't need anything like checkpoints in the end. But I think the use cases that are stateless, that are not stateful, some users have them when they start, but most users tend to outgrow them really fast.
Well, let's take a question from the community. Vasilis is asking, are you working to add any adaptive methods like adaptive random forest into evolving data right now to any of your projects?
I think it's a bit of a specific use case. So from from what Flink is, it's basically a it's at this point it's a processing system, fairly use case independent. It does have a few libraries. It does not yet have a full-fledged machine learning library where, for example, you would have some of these algorithms. There are a bunch of ecosystem projects around Flink. There is a project called A-Link, which is a collection of I think like almost 100 different machine learning algorithms implemented on top of Flink. It might be that, for example, some algorithm like that exists there, but I'm not deep enough into that project to actually say this with certainty. But if you're interested in that general space, I would check this out. So yeah.
And so on that note, since the topic has been raised, what are the machine learning use cases or scenarios where you see Flink sort of supporting advanced machine learning? What does that look like currently today?
Yeah. So I think on the machine learning side, it always makes sense to look at two different sides. There's the side of training a machine learning model of let's say that's the part that the data scientist does, like going through modeling parameters, tuning the model, evaluating, coming up with something that you're then happy with and you want to deploy. And then there's the side of let's say very often the data engineer that takes this model, integrates it with the application, and then as the user comes, the model spits out the recommendation. I think the holy grail kind of is to have a unified way of doing this, to say, okay, once you've built the one side, you can just like push it to production and the other side runs as well. For some simple use cases, that's quite doable. For the more complex ones, you also need also need a bit of data processing work on the application side. A good example is a lot of these fraud detection use cases. Let's say when a credit card transaction also comes in, you usually don't look at it in isolation and try to label it as fraudulent or valid, but usually take a lot of history into account from that user, between the geographies. What do you know about these partner banks? What's the histogram of payment over the hours of day that like these users usually had, and so on. And that's, for example, where Flink is used a lot, like to assemble this information in real time and supply it to the machine learning model. So that's where we've started off with Flink, like the you can say the model evaluation side of things. I mentioned it a bit earlier when we were talking about Python. There's some people in the community that are very interested in extending this to the model training side and evolve it towards a system where you can do training and evaluation basically in a unified way. I think that's a very exciting perspective, but I think this is going to need a bit more work at this point. So
got it.
Yeah.
Very interesting. So let's go back to some of the things that I know you're excited about in Flink right now. We've talked a bunch about the architecture. We've talked a bunch about the basic features and the unified analytics, which is unified stream and batch. What about this concept of stateful functions? Can you talk to us about that and what the power of those are?
Yeah, definitely. So Stateful Functions is a pretty new project, so a sub-project in Flink. Can think about it like that. Yeah, so maybe to explain what the idea behind Stateful Functions is, let's look at a few like core characteristics of data streaming, or at least the way that most data streaming systems, be that like Flink, Kafka Stream, Spark, and so on, work. So what these systems do is they let you define a streaming data flow, meaning sources where the events come from, and then like a directed acyclic graph of streams and transformation operations through which these events flow. And then these transformation operations might be anything from filters, might be joining, aggregating, enriching, and so on. But you have a pretty like rigid predefined flow, and that is also, I think, important, because that flow captures like a bit of the interaction topology. Having a directed acyclic graph is also important if you want like these sophisticated time models of event time and processing time trade-off, and so on, because time kind of progresses then also as you go through the directed acyclic graph. Stateful functions, on the other hand, tries to drop a few of these assumptions. So why would you drop that? It tries to actually capture some of these use cases that are closer to the, let's say, not the core data processing side, but more the event-driven application side. So let's say use cases where folks like to use, let's say, things like actor system or other event-driven stuff, RxJava. I think there's a lot of merit in some of these abstractions in the event-driven application world, but I think there were a few very core things missing, and that is this notion of consistent state in there, which is something that actually Flink has solved very well on the stream processing side. So Stateful Functions is really trying to be the bridge between, if you wish, the stream processing world on the one hand, and the, let's say, reactive stateful application world on the other hand. So it's a form of event processing that drops a few notions of stream processing, like being restricted to DAG and instead have dynamic messaging, and thus makes it a bit more accessible to reactive application developers. So Stateful Functions is, if you wish, a blend of actor programming and stream processing.
Okay, got it. Well, someone else had a question that I want to go back to. He actually wants to go back to state. How do you handle large states in Flink?
Right. So Flink is actually able to handle pretty large states. So if you look at like what is one of the largest known use cases for Flink is I think this online recommendation system inside Alibaba, and when they have their crazy shopping holiday, I think the system carries up to 100 terabytes of state inside the stream processor, which is a lot, I would say, for pretty much any database. How does Flink handle state? So first of all, it's a parallel, it's a sharded system. So when you have states usually organized by key, and it belongs to a key, and that state, it might be the parameters associated with the user for their specific for the recommender to issue recommendations on that user, or it may be associated with the join. So it's the occurrences of an event for that key. So if you want to join this with another stream and an event with the same key comes from that stream, you can look up what events happened in the last 5 minutes on the other stream, so you can join in and combine them. And so first of all, state is sharded by this key, and the streams are also co-sharded by the keys. And then inside each shard, Flink uses RocksDB to materialize the state and make it accessible by key. And then it actually integrates this checkpointing mechanism with RocksDB. There's a pretty interesting way. RocksDB is organized as a log structured merge tree, so you can actually create immutable point-in-time snapshots from RocksDB without actually stopping the database. You can just continue working it, but you can pin, if you wish, like a point-in-time snapshot, and that's what Flink does during its checkpoint. So it actually creates these snapshots when the Flink checkpoint runs through the operator, and then it basically diffs this with the previous checkpoint and uploads the delta between this and the previous checkpoint. And that way it can actually scale up to a pretty large state. So it can have like tens of or hundreds of gigabytes in some cases, even on a node, because it only incrementally needs to upload the changes during checkpoints. What you have to bear in mind though is if you handle very large state, when one node really physically crashes, recover it on another node, you need to kind of pull the state to that node. So this node is going to have a bit of a pre-warming time before it can continue processing, just because it needs to like pull all these gigabytes back into the local RocksDB.
Got it. Someone else has asked a question about deployment, which I'm excited about because I wanted to talk to you about that next. What is the current and future recommended way of running Flink on Kubernetes via Beam, which Beam supports Flink as a runtime, as I understand, or some other way. So let's talk about deployment for a second.
Yeah. So how do you deploy Flink? There's actually a lot of answers to this. This is partially due to the fact that the set of use cases is so wide. So if you'd like to deploy, let's say, a real-time streaming application, I think the recommended way I would say is just use Flink on Kubernetes and deploy Flink as an application. What does that mean? Maybe taking a step back, Flink has a few different ways you can think about it. You can think of Flink as either a cluster of, like a set of processes you bring up, and then you can send them work. Let's say the classic Hadoop Spark style or so, where you start your processing cluster and then you can open a console and send work their way. Or you can basically say, here I'm taking this application, putting it in a Docker image, and then telling Kubernetes to start so many replicas of that. And then this is basically it behaves like a self-contained application. You don't have nodes that you can then later submit other work to. And this is a bit of a, I'd say, two different approaches to deployment that come from the fact that Flink tries to actually offer users a natural way to do the batch processing style work and the stream processing style work. And I think this deploying something pretty much like a natural application of Kubernetes is something that a lot of the stream processing users really like, versus configure a cluster, bring it up, be that on Yarn, Kubernetes, or so on, and then being able to connect with a client tool and submit individual jobs that might be short-lived is something that a lot of batch users like to do. So it kind of allows you to do both things. Maybe coming back to the original question, for the streaming world, yeah, there's a pretty natural way to deploy a Flink application on Kubernetes by extending just the Flink image, dropping user application jar and copying it in there, and then just deploying this on Kubernetes. And
what about the Beam runner, the Flink runner in Beam?
Yeah.
Explain the uses of that and sort of what's the sweet spot there? Are those for folks who are presumably already running on Google Cloud, or are there other meaningful use cases there in terms of sort of optimal deployment?
Right. So Beam is mainly a unified API, and it's not just an API. It's a very big project with there's the data flow API. There's also a SQL layer on top of that, and there's like lots of connectors to various runtimes. To Beam, Flink is mainly a runtime, similar to how Google Cloud Data Flow is a runtime to Beam. So a user writes an application against Beam, and then they can choose where to run it. Do they want to run it on Flink, or do they want to run it on Google Cloud? Do they want to run it on Storm? Do they want to run it on Samza? Do they want to run it on Spark? There's lots of different runtimes with a differently, let's say, broad coverage of the feature set. I think Beam is interesting when you want to go for something like a let's say hybrid cloud strategies, or if you're, let's say, a bit hesitant in committing to a system, right? If you want to develop the application and you think like, okay, I'm really interested in trying out this, but I might eventually migrate it to the cloud anyways, go for a managed service there. Then Beam gives you this abstraction layer. A little bit like you could think of SQL being a language that is cross compatible across different databases. So you write your analytics logic in SQL, and then it doesn't matter if you run it on Postgres or on MySQL or on Oracle or so. You can choose what the underlying system is. So Beam tries to do exactly that. And I think this this is a very interesting. It's a very interesting interesting approach, and particularly interesting for folks that, let's say, have parts of their workload in the cloud, let's say on Google Cloud, and parts of their workload, let's say on-prem, where they, for example, would use Flink as the underlying execution runtime.
Got it. Well, one more follow-up there. If you don't have a comment on this, it's no problem. But where do you see Pulsar when compared to Flink? Pulsar obviously is one of the newer streaming projects. I believe was that related to the Heron project, or is that something separate?
I think yes and no. I think it was commercially related to the Heron project. Technology-wise, not strictly. So on the streaming side, there's different layers also you can look at, right? There's, if you wish, there's the streaming storage and transport, and then there's streaming computation. I think you can draw a parallel to the batch ecosystem, where there's batch storage like HDFS, S3, and so on, and then there's batch compute like MapReduce, Spark, Hive, and so on. And Pulsar and let's say the Kafka broker side and so on, they're on the storage side of things, like, you know, the streaming equivalent of, if you wish, HDFS and S3 and so on. And Flink and Heron and Kafka streams and Spark streaming, they're on the computational side of things, like you know, like Spark and MapReduce and Hive. So in that sense, it's not easy to compare Pulsar directly with Flink, because Pulsar is predominantly storage. It has a little bit of a complete compute side with Pulsar functions, but I think it's a very specific, limited one. Versus Flink is really a compute system that is usually complemented with a streaming storage. So yeah, Pulsar and Flink actually can be used pretty well together. There's a connector between the two systems. There's actually a bunch of companies that do that. So
got it. Very interesting.
I think Pulsar's main, you know, equivalent system would probably be Kafka, to compare it against.
Understood. So Rick is asking, is there a roadmap for expanding PyFlink user-defined functions to make them more suitable for ML-oriented Python functions?
Right. So that's actually a great question. So I said in the beginning, the initial support for Python that we started with was with like user-defined function in the table API, and there's a different set of user-defined function, like aggregation functions, scalar functions, table functions, and so on. And that's the one side of it. The other side of it is like, how do you know, what kind of environments do you support the execution, and do you support environments where you have access to like native libraries? How do you interplay with, for example, other libraries in that space, like or other APIs like pandas or so? I think on both sides there's quite a bit of work on the Python side. So there's definitely a lot of work to broaden the type of functions that are supported in the table API. There's even work on adding Python support for the data stream API, so you can actually write like very general purpose map, flat map, process, window functions in Python. And on the other side, to add more support for different interpreters, easier interaction with existing native libraries and so on. I think the very best way to get the details for that is actually on the Flink website. In the wiki, there is what we call Flink improvement proposals. It's basically the list of big features. It's probably the best way to look at the roadmap. And there's always some flips in each release that talk about the extended support for Python. To be quite frank, that's also the place where I would go to look up the details now.
Are you happy with the level of Python support from the community so far, or are you looking for additional committers?
I think the Python side would be happy to take on a committer or two. Yeah. It's one of the newer features, so it's I think less than a year that the Python support exists in Flink. So these newer features, yeah, they usually tend to take a release or two before they start forming up like a real user and committer base, because once a new version is released, it also takes usually a bit until users pick it up, then until they've tried out enough to really get back to the community, get involved with, okay, this works, this doesn't work, and so on. So yeah, I would actually say that the Python side's it's a pretty good side to get involved in if you're interested in being active in the community. Maybe
Great.
maybe joining.
That's great. That's great to know.
Yeah.
Well, we're essentially at time, Stephan. This has been a great conversation. I just wanted to ask you before we leave, what are you most excited about on the roadmap for Flink going forward?
That's not an easy question. There's a lot of stuff happening always. It's hard to choose. So there are a lot of things in the current and in the previous release that I was really excited about. Maybe let me start with that. Some of these excitements already come to a closure, if you wish. So this extension of the streaming of SQL and streaming SQL coming together, like I tried to explain it earlier. This is something I find really fascinating and very cool. Like this is a very big deal. Combine this together with like the change data capture support that Flink 1.11 added, and you actually have a pretty neat story from from attaching Flink to a mainframe or another database, grab changes of the log, compute materialized views, and store them in another system. So like basically building an infrastructure around like services on materialized views. This is an extremely cool thing. We already talked about the Python side of things. Definitely very nice. What I like in the features we're working on at the moment is, I think we're very short before kind of closing the circle on the batch streaming unification, also on the data stream API. The batch streaming unification works pretty well on SQL and on the table API. The data stream API, as basically the earlier API that we had, has a few things and has a few things in there that do need some work in order to make this work equivalently well on the batch side. And also the data stream API not going through an optimizer means that we can't rely on something that magically now changes execution models between batch and streaming, like I explained before, but we actually have to come up with a different physical way to translate these operators between batch and streaming. And we're very close to actually completing this. So there's this is something we're working on for this release. So I think that's something I also really like this, like rounding up this story. There's a little bit of work we're doing on the fault tolerance side, and like without saying too much, because this is not all of that is yet beyond the, let's say, research and prototype stage. But there's a few things we're working on in that area that I think are going to make a pretty big difference. It's some of the biggest changes we're doing in the system, or we're researching in the system, since Flink actually started with streaming and introduced the checkpointing model. So with the ultimate goal of really making checkpoints very robust, very fast, speeding up recovery by orders of magnitude and so on. And there's some stuff that we're going to see being proposed to the open source community in the next months that I'm very excited about.
Awesome, that's great. And last question, what surprised you most about your work on Flink over all these years?
What surprised me most? I mean, very, very high level speaking, the fact that, you know, this prototype that a few students at university stitched together actually was interesting enough to form in the end such a big community and user base. That is fascinating. That I still sometimes don't get quite over that. The other part, yeah, I don't know how many things do in the end come together in such a nice way under this streaming umbrella. I said this at the very beginning. Like, streaming is a bit of a nice unifying paradigm for various things. And I have the feeling the more we work on this, the more it actually shows in almost every layer of the system, not just like in the APIs, but like also in the runtime. You start to work on something, and then you figure out, like, okay, there's something that doesn't perfectly work, and you see, like, okay, we're actually doing it a little too batchy here, and, you know, if, like in a pure streaming way, you do it like this, and then you pull it through, and like all of a sudden everything works super well. And it works super well across the batch and streaming side. So this, yeah, there's really I think there's a beauty in the streaming paradigm if you see it completely to the end, in both in the conceptual and in the implementation layers. And I think there's like, we as a world as a whole haven't actually really reached that point where all of these things come together finally. We're getting bit by bit closer. Like, various projects are working on this, Flink being one of them, and I think it's a pretty cool thing. It's going to be a big impact on infrastructure for the future when we see this come to fruition.
Well, thank you for being such an evangelist for the streaming paradigm, and for being so eloquent in the way that you describe it. Thanks for all your work on Flink and the community over the years. I think it is a true example of a amazing community project, which we love to support here at Data Council. And I'm hoping that you'll pick up some more interested users, some contributors from this conversation, and that it will be helpful for you in the Flink community. So thanks for joining us, Stephan. It was great to have you here.
Yeah, thank you very much for having me. It was a lot of fun. It was a great discussion. Thanks so much.
Thank you, and thanks to the rest of the community for all your questions. We'll see you next time.
Bye-bye.